And with
All right.
that, over to you, Aaron.
Awesome. Thanks, Ian. Yeah, so let's get started and learning as much as we can about transformers within the next hour and 30 minutes. So here's the agenda for today. We'll start by going over some prior state-of-the-art research in NLP with regards to deep learning. We'll also go over some issues with these types of prior model architectures and maybe what we can learn from them and where the transformer comes in. This will lead to us actually talking about the transformer, a brief overview of the transformer, this idea of self-attention, right? This name of the paper is called Attention is All You Need, right? What does that really mean? As well as some other key differentiators of the transformer model architecture. Finally, we'll conclude with really what's next, some current research fields that utilize transformers, as well as some key recent applications that utilize this new architecture, and lastly, how this is relevant to Alation. I like to start off with kind of a one sentence broad summary of like why transformers are important. And I'll kind of reiterate this throughout the entire presentation, but transformers are just a new type of a neural net architecture that allows for parallel processing, long-term memory, and improved performance, which sounds pretty great, right? So it's great for everything. And I'll continue to reiterate why this is and why it's just such a great architecture as we continue throughout the presentation. So let's start with some prior research and learn more about what task we're actually trying to solve here. So the task that we'll look at today is seek to seek. So what that means is you're inputting some sequence into your machine learning model, doing some processing on that sequence and outputting some sequence, which can be maybe a prediction or even a classification. So this could look like maybe machine translation if you're trying to map an English sentence to a French sentence, or even something maybe like code generation where you're inputting in natural language and trying to output syntactically correct code. So the question is, what is this model, right? What goes in here? Well, if we look in our tool belt for deep learning, we know that we have the feed-forward neural network, which I'm sure you're all familiar with. It takes an input, does some, broadly some matrix multiplication, some activation functions, and maps your input to your output label. What's important to know about this is that you really only allow signals to travel unidirectionally, right? So you're mapping a relationship from input to output, right? So there's really no feedback, no memory. The issue with this is that when we're looking at sequential data, there's more than a relationship between your input and your output, right? There's also the relationship between input to input. If you think of a sentence, right? Each word also has a relationship to all the other words, right? In that case, in an English word or in any natural language, that would be called syntax, right? So a feed-forward neural network isn't very good for that. So then came along the recurrent neural network. And how this works is you can think of this as kind of a sliding window throughout your input sequence. So you input maybe the first token, and that gives you some output. And then you process the next token. But instead of just processing the next token, you also take the output from when you process the prior token and input that. So now you're not only getting information about the current token you're at, but also all prior tokens, right? So a more intuitive view of this is this unfolded architecture. So if we have some input X, right, we input X naught in, or let's just say X sub T into our recurrent neural network, and it outputs some H, right? Well, when we process X sub T plus one, we're not only putting that into our neural network, but we're also putting in H sub T from the prior processing, right? So we're getting current information from our current token, as well as information from all the other tokens prior, right, from when we process that. So that's great. We know how to process sequential data, and it works pretty well. There are many variants of RNNs, like LSTMs, if you've heard of them, GRUs. We won't get into that. They're very similar flavors of the same thing, just processing sequential data. So question is, let's go over another example, right? So let's ask the model, what time is it, right? Well, this is really just a sequence, right? A sequence of characters or of words. right? So we can break this up and we can process each token one at a time, right? So we'll process what, and that'll create some output, right? And next, we can process the word time, right? So when we process some word time, we'll also take in the output from the prior step. And so that kind of bakes in the knowledge of not only time, but also what, right? And so you can continue doing this kind of recursively down the line, right? RNN, recurrent neural network. You do that going down the line. And what you'll see is our final output, O5, has all the information, the entire sequence kind of together in one matrix. And we call O5, the final output, our context vector. So it has learned information from the entire sequence. And that's really, really great, right? So now you can turn that context vector, you could maybe put that into another neural network, like maybe a feed-forward neural network, and do prediction on that, because now we have learned information on the sequential data, right? So that's great. And so this new new architecture, it's really quite old, allows us to process sequential data. What are some issues with RNNs, right? Well, I think probably the most obvious one is that we're not really using any parallel processing, right? Because we're processing each word one at a time, right? If we're inputting token x sub t, well, you need the output that came from x sub t minus 1, right? And so that's a huge issue because with the advent of GPUs, easier accessibility GPUs, we're not really using them at all with these RNNs. The next thing is this idea of vanishing gradients. We won't really get into the technical aspect of backpropagation through time, but the main idea is the following. If I give an example, John likes Jane, he bought her flowers. If we look at the word he, right, according to our RNN, the word that is most impacting the contextual meaning of the word he is the words that are closest to the word he, right? So in this case, it would be Jane, right? Because it's the closest, and it's, locally, just it makes sense because you're kind of going sequentially down the data. Well, in reality, you really shouldn't be looking at Jane, right? You should be looking at John, right? Because he refers to John, and we see that. It's very intuitive to us, but not intuitive to the neural network. And so that's not quite correct. And so we want to find a way where our model architecture can learn kind of as much as it can from prior data. So have this idea of long-term memory. Great. So this kind of allows us to transition into transformers. And I see there's a chat. I'm not sure if that's.
I was just putting an even more pathological case in there. You can keep
Oh,
going.
yes. Okay, great. Yeah. So we'll move on to transformers now and kind of see how it fills the gaps in for the RNNs. So again, I kind of want to stress this quote here. Now it hopefully should make more sense, right? We can allow for parallel processing, long-term memory, improve performance. Well, how does it do that? Well, again, we'll go to our seek-to-seek task. Instead of just some random RNN model, we have the transformer, right? So we'll be looking at translating French to English, right? So let's look under the hood of the transformer, understand what's going on. Transformer is made up of two sections, so really two models, the encoder model and the decoder model. There's nothing special about this type of architecture. You can do the same thing with RNNs, where you have like an RNN encoder, which kind of learns the French sentence, like kind of what does the French sentence mean, right? Get a contextual representation of this French sentence, which turns into basically just for the machine or for the model, just a giant matrix of numbers. You take that, feed it into the decoder, and the decoder will map that contextual representation and turn it into what we know as English, okay? So let's look at really what makes the transformer so outstanding. So let's look into the encoder. So we look in the encoder, we see something called self-attention, the self-attention mechanism. And again, if we were to erase self-attention and replace it with RNN, it would just be a normal RNN architecture, right? You input your input sequence into the RNN, and then you get out some context vector, and you could put that into a feed-forward network. So nothing different there. The difference is this self-attention, and I would look closely at how we input these input vectors. Notice how we are putting them all in at the same time, right? As opposed to an RNN where we go one at a time. Well, how are we really doing that? And really, what is self-attention? So let's go over kind of a high-level view of what self-attention is doing. So what this does is for each token in our input sequence, okay, we learn how important every other token is for the contextual meaning of our current token. So if we look at this example, right, we'll see the word, the model has learned that the word it, the contextual meaning of the word it is most signified by the meaning of the two words the and the word animal, right? Which makes sense because it is referring to the animal, okay? So as opposed to just learning contextual representations by what words are locally close to our current word, we're just taking everything in and trying to learn how to weight the what our current word should attend to, or what is most impactful for our contextual meaning here. Okay, well, how is it doing that? I don't want to get too in the weeds of the technical details because I just think it's probably not necessary for this presentation, but I'll kind of go over it briefly. And if we want to talk about more about it after the presentation, I'd be happy to do so. But really how it works is if we have some input sequence, which in this case it's 2 by 4, which tells us we have 2 words and the embedding size is 4, right? We're going to multiply them by 3 weighted matrices, and these are learned. That gives us our Q, K, and V matrices. And again, not really too important for this, for the high level view, but we can use these Q, K, and V matrices to learn some attention score known as Z. And you can think of this as kind of the context vector of the RNN, except for the transformer. And kind of intuitively what's going on here is you can think of Q as everything that we know currently about our input, right? And then you multiply that by K, and you see that that's going to be a 2 by 2 matrix, right? And of course, if you look at our vocab size for our current input, well, there are 2 words, right? So what it tells us is for every word, how close attention should we pay to each other word, right? So it's 2 by 2, right? If that makes sense in terms of dimensionality. Then we do some, scalability, dividing by some number to make sure the numbers are small enough. We softmax it to get the numbers between 0 and 1, and then we multiply by some V. And you can think of the V as kind of our original input, and we're trying to basically weight out or filter out what is kind of important or to attend to for every word. And that gives us our final attention score, or you can think of it as our context vector, okay? And so this, we'll do it many, many times. The architecture given in the attention is all you need paper will do this multiple times, just try and learn multiple attention ideas. But once we finish, we'll get to the decoder, right? So now that we've learned kind of how to go from—
sorry, Aaron, real quick.
Sure.
Would it be fair to abstract the prior a sort of array or matrix multiplication, excuse me, to basically at the end produce a input tokens by input tokens table where you basically got a value for each of how much it depends on or relates to or requires attention to each other?
Yeah, so that would be for the dot product of Q and K, right? So because if you look at just the dimensions of Q, it's 2 by 3, and then K transform be 3 by 2, right? You multiply that, you get 2 by 2. And so you can imagine this 2 by 2 matrix of where it'd be like thinking. And so in this case, the input sequence is thinking machines. It'd be thinking machines by thinking machines, right? And so you can think the top left element would be, okay, the word thinking machines should pay this much attention to this other word thinking machines. And of course, that would be called self-attention, right? Because you're attending to yourself. So it'd be quite high, right? It'd be like maybe 0.8 or something like that, right?
Yeah, yeah. Yeah, but in a real life scenario, right? Like if we have, John likes Jane, I'll just stop there, right? That there'd be some cell for, John to John's very high, Jane to Jane's very high, and the hope would be eventually get to a place where he to John is
Right,
very high. And
right.
just one more thing, can we just go back one slide? I just want to make sure I'm following before we get more complexity.
Sure.
Um,
Uh,
that effectively in that cross product you're describing, this is basically showing one row. This is or one column, right, for the word
exactly, exactly,
okay, good.
exactly right.
I think I get it well enough to
Yeah,
follow. Thank you.
yeah, great. That was a great question. Yes, I know it can be really confusing, and thankfully it's kind of all done under the hood now as there's the advent of transfer learning. But we'll talk about that later. Yeah, so that will come out of our our encoder, right? Kind of everything that's baked into this learned matrices. And we'll take that, we'll put it into our decoder, and it'll do exactly that. It'll decode what the machine has learned and learn to turn into this contextual representation, which it showed as a matrix, and learn to turn that into actual English. Now, I know that's kind of confusing, right? How are we turning this matrix representation into like actual English? So we can kind of zoom in on where we're bridging the gap from the decoder to this linear layer. And again, I should be noted that we kind of continue this decoding until we hit like an end of sentence token, right? Then it tells the model, okay, we can stop. And then this is kind of our predicted output sequence. Okay, so let's kind of look at this bridging of the gap between the decoder and the linear layer. So if we look at this, we have the decoder stack output, right? So that's going to be kind of what we learned from going from our encoder output plus our what we predicted earlier from because we also take in this decoder, the previous output here, right? So we take in our context plus what we learned from the encoding, take that information, again, just some form of self-attention, and then process that in a linear layer, and you get the output continuously. Okay. So this output, this decoder stack output, is run through linear layer, right? You output some logits, right? You can softmax that, and what you get is a distribution of probabilities, or a probability distribution of how confident the model is that the next prediction should be some particular vocab, right? And so this prediction final vectors of size 1 by vocab size, right? So each cell is one element in our dictionary. And there are many ways things that you could do here. In this case, we argmax. So we just find the highest probability word, right? So that our prediction should be, and that's what we'll just output that. But you can imagine for something like autocomplete, we would maybe take the top 5, right? And we'd output that. But that's kind of the intuition behind kind of how we're bridging the gap from this decoding to this linear layer and getting actual English output, or whatever output we're going for, but in this case, English. Okay, last thing I should cover is the loss function. Like, how are we actually comparing our trained model's output to the ground truth, and how are we calculating loss and then training and learning from there? So it's very similar to any other neural network architecture. So what this is showing is that each position, the model is like X% confident after, remember, soft maxing of this current prediction, right? So it's 93% confident that at position 1, the word should be I, right? And then kind of so forth. So these are the predicted probability distributions. And then we have the target model output, right? Well, they should be 100% confident that the first word is I, because it is the word I, right? And so I think from here, it's now clear that you can use any type of loss function. The paper uses cross entropy loss function, right? But yeah, you can just subtract, find the difference between these probability distributions and calculate loss from there. And that's kind of a very high level overview of the technical aspect of transformers. Let's look at some impacts that the transformers are having. So the first architecture that is really coming about from these transformers is BERT. I'm sure you've all heard of this this model. What it does is it takes the transformer encoder, right, which uses this self-attention mechanism that we discussed, and it takes this input and masks one of the words, and it will take that, put it through the transformer encoder, and that'll output again this kind of context vector, right? And you can take that and put it through a feed-forward neural network, and it'll predict, try to classify exactly what word that masked word should have been, right? And then it'll back propagate. And what you'll learn is these amazing word embeddings, right? So what it's doing is it's mapping these words into an embedding space, right? Or Euclidean space. It's learning these really kind of colorful representations for these words. And it's now state of the art. And anytime we use word embeddings, it's almost always BERT. Also GPT-3, I'm sure you're all familiar with GPT-3 and its kind of long-lasting kind of works and consequences and applications throughout the machine learning community. And all GPT-3 is really transformers just stacked on top of each other. And I think the largest GPT-3 model has 96 layers, and I think it's 175 billion parameters. So it's very large. And data set, of course, is very large. And this has allowed for a lot of transfer learning. You can like access the GPT-3 API and use this trained model to do a lot of downstream applications. And finally, I should mention, there have been a lot of applications and architectures outside of BERT and GPT-3 that rely on these previous architectures. For example, BERT is open source. So many researchers in academia, especially Stanford and Carnegie Mellon, have used these architectures to create their own downstream applications. We see this a lot in genomic analysis, code generation, document generation, machine translation. And here, this graph just shows that since the kind of release of GPT-2 and these other new architectures, we've seen a huge spike in the performance of NLP tasks. Superglue is stems from a previous data set in NLP, but it's kind of the benchmark for how well these models perform on difficult NLP data sets.
I just want to point out the x-axis here. The introduction of superglue was because the glue benchmark had been considered essentially solved, human level performances or greater. They introduced superglue, and within a very short period of time, also reached human performance.
Great, thanks. Great. Well, let's go over some limitations of these transformers, and really this will be focused on the large transformer models that we've kind of seen that we just kind of went over. One of them is the increased training time. So in calculating like these context vectors, we use these training weights for each of the encoder's time steps. And that can be a lot of weight parameters. If the input data for the encoder is really long, for something maybe like text summarization, right? The input sequence for that's very, very long, and you want to try and output a very small sequence. And so this is just some small fact, like it would take 355 years to train GPT-3 on a Tesla V100. Obviously, GPT-3 has already been trained, so we could just use transfer learning, access the API. So all our hard work's been done for us. It's also very data dependent. You need a lot of data to train transformers. And the reason for this is because you just have so many parameters, right? There's so many parameters, especially if you're stacking all these encoders on top of each other. You have your K, Q, and V vectors, and then there are also many variations of transformers where you split up these vector matrices, and you have many of these matrices. And so GPT-3 has 175 billion trainable parameters. So just to keep that in mind. And last thing is that it's can be very expensive to train. GPT-3 itself took approximately $12 million to train. Again, not something that we would have to worry about immediately. If we were to employ transformers, we would use some form of transfer learning, but definitely something to keep in mind for the higher end models that places like Google, Microsoft, and Facebook are coming out with. Okay, so our final thing is we'll talk about what's next, what are the current research fields and research applications, and how this is all relevant to Alation. Okay, so some recent research fields have been really large improvements in machine translation. I should note that a lot of this has actually been solved with transformers. I mean, the performance for machine translation has just actually outpaced the human performance recently from the superglue benchmark. But a lot of these architectures in machine translation have trickled into code generation. And so what this looks like is saying inputting something in natural language and outputting the correct code syntactically. And this is a different type of task because not only do you want the code that you write to be syntactically correct, but you also want to output what it was meant to output, right? So you have kind of two different hurdles, right? Whereas maybe from natural language to natural language, you could get away with, there are multiple ways of saying the same thing, right? So these are kind of two separate tasks. We also have question answering. And so this is probably the most cutting edge of all of the research fields right now. It's very much so unsolved. And the idea is that you want to be able to input a question and just output your answer. And so again, this is very complex. Right now in the field, we see a lot of different architectures kind of molding together. So usually you take this query and you encode that and you map that into Euclidean space. You do usually some nearest neighbor matching to find the documents that are relevant to this particular query. And then you can encode those specific documents into the transformer. And then from there, you can get your answer. Again, kind of glossing over, but that's for the past like 2 years, that's kind of been the way to do it. So splitting up into document retrieval and then question answering. Finally, we have document generation. And so this, I'm sure you've seen all over Twitter in the past like 2 or 3 years or so, GPT-3, right? You can input like a large like part of a document, and then GPT-3 will continue that document, right? And the way that this works is instead of ending on like an end of sentence, you can continue the transformer's decoder can continue to predict even after the end of sentence token. And usually that's up to the user, right? You can choose how many tokens to generate. And so that's also been really interesting to see what the GPT-3 can actually write and if they can write articles of good quality. Yeah, and so our last thing is relevance to Alation. And of course, potential transformers are endless. And so there are plenty of tasks that we can use at Alation to solve using transformers. Just briefly, I know Aaron's familiar with Texas SQL, right? And then many other things like sentence completion, article summarization, taking large articles and encoding that and decoding that into very small sequences and putting a limit on that sequence, and so many more as well. And so with that, yeah, thank you. And I think I'll pass it off to Ian for maybe a little discussion.
Thank you so much, Aaron. That was really great. I really appreciate that. Yeah, so there's sort of unlimited things that we could talk about at this point, and I do want to open it up. I figure there's sort of two main things we can talk about: the technical side of transformers and their implementation. Maybe we can talk about that first, and then bring it out to more general discussion about Alation as a product. So does anyone have any questions about the details of transformers before we move on to sort of higher level discussion, or really anything about the technical stuff that was discussed today? Or maybe something you read in the paper that you were a little confused about and you wanted to bring up? No?
I mean, I think for, at least for me, it's like all fun and games when you're reading about it and you're like, cool, yeah, not. And then like, I think it'll be really interesting when it gets to the point where, Aaron, you're like working with our data and we understand what it actually means to implement this. So I think that's kind of where I'm at. I'm like, okay, I can kind of nod along and understand, what the components are doing and, why one, feeds into the other in that way. But like, if it was like, oh yeah, and now you're going to do the text to SQL, for example, like, what does that really mean? Like, I think that's like the next level and I'm definitely not there yet. So yeah.
Yeah, and that's definitely something that, we want to sort of start with this discussion so that we can explore into those specifics that people are really interested in, use this as a platform to gauge where people would like to see this discussion move forward toward, because there are so many possibilities. There are a couple technical details I do want to point out before we move on. Aaron, if you can go back to the BERT slide.
The third slide?
BERT.
Oh, BERTs, sure.
Yeah. I'll just use this as a, yeah. Yeah, so there are a couple things that I want to point out about all these technologies, transformers being one of them, BERT encodings, and one particular aspect of the way that we train language models today. And here you can see that this is the transformer encoder path, right? And it's just using a masked version of the input. What does that mean? What is the consequence of that? Well, it means that you don't have to have a matched language pair output, right? You don't have to have matched corpus to work with. Essentially, what this training methodology gets us, and the encodings that you get out of this, is a self-supervised or unsupervised, depending on how you look at it, training methodology, which really has opened up the floodgates of our ability to create representations of language from all of the available text that we have. Because supervised learning methodologies where you need an input and its label, or an input and its human translation to do a translation, means that you are limited to a much smaller amount of data. And as we all know, these neural networks just feed on data. So we have the ability to make use of orders of magnitude more information to train these models. That's part of the reason why they're so big, is because we can actually capture the long tail of information off of the web. For example, when we did our GPT-3 based hackathon, we were using a piece of the long tail of the web where this model had already captured how to go from a natural language description to some basic SQL, right? That was embedded in this gigantic model just by virtue of the fact that it was able to train itself in a self-supervised way on pretty much all of the contents of the web. So there's the transformer, which makes that technically possible because you can do parallel training across an entire sequence, use the full computational capacity of a GPU, for example, or a farm of GPUs or TPUs. And then there's the training methodology that they've made use of in this masked language model. And then again, as Aaron mentioned, once you have these trained embeddings, for example, you cut out the entire really middle of this encoder platform and just say, okay, I have this word, what would BERT say its encoding is? You can use that even in smaller architectures and say, okay, if I were to take this word in this context and embed it in the meaning space of all language, how would I represent that? That is the word embeddings that BERT gives us. And these embeddings, like word2vec or glove embeddings before it, has also opened up a huge amount of possibility, because you can put sort of smaller networks on top of that after it's been trained and get a surprising amount of quality. For example, you can combine the old technologies of having an RNN on top of BERT embeddings and do pretty well with a much smaller network. And of course, you can do fine tuning on top of the large networks, or like we did with GPT-3, they have this strange capability of already having seen so many tasks, because humans describe tasks with language, that they are often described as single shot, zero shot, or few shot learners. You just give it an input describing the task, you give it the start of your task, and you say, what is the completion? For example, the underlying prompt for our hackathon project said, we are translating English to SQL, and here's the schema of the table that we are working with, and then we would feed in the English language, and it would use all of that context and its knowledge gained from information across the web to do its output. So there are a number of different things that have combined along with transformers to really revolutionize natural language processing and open up the floodgates in terms of just destroying benchmarks across left and right. Okay, with that,
how standardized are encoders? Like, if you were saying, like, you do your French to English translation, if you just had a different decoder that did whatever that intermediate step is to German, can you then, like, does it then do French to German, or do you kind of think about each problem separately?
So yeah, so in the largest language models that have been trained on corpuses that include multiple languages, they do have a small ability to do translation from one language to another. It's not nearly state of the art. Most state of the art language machine translation models are trained specifically on one-to-one language mappings, but there are also language models that are one-to-many or many-to-many, and it really does depend on what your training data is, what the task is that you give the model. Hopefully that answers that question.
And maybe I can give some insight to that as well. Like, yeah. For something like GPT-3, right? It can do like English to French, and then also like French to Spanish, right? Which is crazy because it wasn't necessarily trained on these tasks like specifically, right? But the reason it's able to do this is because its model is just so large, right? Remember we talked about the encoder being the part of the model that goes from these word embeddings, which are just the words, and turns them into some contextual dependent matrix, right? So that pretty much will stay the same. But when you take that and put that into the decoder is responsible for turning that context vector or matrix into the actual output. Right? Because these huge models just have so many decoders, and these decoders are huge too, then there are kind of like neurons within these large models that kind of are activated when, or they're trained and activated when you learn these specific tasks, just because they're so large, which is kind of why large models are able to do multiple things. Ian, I don't know if there's anything else you want to add.
I will point out, if you go to the limitations, one of the important things from a product perspective, at least, is that the outputs of these language models are probabilistic. They're not rule-based, which means that you always have to consider the possibility, one, that it's going to output something unexpected. Two, it's going to output something which violates sort of elementary human expectation. It will less and less frequently do that, the larger the model, the more it's trained. But there's nothing built into these which prevents it from producing ungrammatical output or nonsense output or repetitious output. Whereas other natural language systems that have built-in, syntactic hierarchies or, parts of speech labelers, et cetera, like those might bound your possible outputs. These are only really bound by their vocabulary and the learned rules from all of the training data. And that's something we're definitely going to have to think about and consider as we use any machine learning neural network-based models in the product, is how to bound them properly, so that we can control the rough edges of their potential output. All right, other questions? Anything even at product level, like what are people excited about in other NLP technologies they've seen? Questions?
Yeah, I am